Hello everyone, my name is Brauch. I'm from Deutsche Wetterdienst and I'm going to present today the work which was done in collaboration with the group of Bodo Arends and with majorly from the PhD student Chang van Pham. I'm going to talk later a bit more about our group, but first on the snowbands. So we have the snowbands, which is a very interesting phenomena, and it happens when you have cold, dry air blowing over relatively warm water. Like it can happen in the Baltic Sea. So what you need is a patch of free lake surface, which has to be at least 100 kilometers long, but it should not be too long. Then you don't have the snowband effect over land. You need this temperature difference between the atmosphere and the ocean to be at least 13 Kelvin. The orographic slope at the coast helps that you have like these really nice heavy rainfalls, and the main season of occurrence is late autumn and winter. The events are very infrequent, and it's hard to get observation of past events. So we looked at the snowbands over the Baltic, but there are also like worldwide, there are other places where you have the snowbands like over the Great Lakes, where it's called then lake effects, but you can also have it over the Black Sea sometimes, I guess, pretty seldomly. So here are some events. I guess you meant the one of 87 or so, 88, yeah, the big one. These are the data which Chang got together of past snowbound events, and so the first are mainly out of literature, out of papers which were cited, and the last one, it was actually recorded by the Deutsche Wetterdienst, and there is a report coming out every month about the current climate state, and so from that one. I brought a satellite image of that period where you can see the snowbands very nicely. This is from the MODIS satellite, and you can see that the cold air is coming from the east and they're blowing over the Baltic, and then you see nicely the snowbands when they hit the land. Then you have like this really heavy snow effect. And for us, it was actually recorded over Germany, where you also had heavy snowfall. But you can also have it a bit over the North Sea sometimes. So what we use to study these events over the Baltic Sea is we employ a coupled ocean atmosphere model, and the atmosphere model we're using is Cosmos CLM. This is a climate version of the numerical weather forecast model Cosmo, and we use it with we employ it for the CORDEX domain with 25-kilometer resolution, and vertical resolution is 40 levels. And we use, for this study, we use area interim data as input data. We couple it via OASIS, via this coupling interface to Nemo Nordic, which we got from the SMHI, thankfully. So we can participate in this development of this ocean model. And here the horizontal resolution is about 3 kilometers. We have 56 vertical levels, and what we did, we ran the ocean model itself for the spin-up period with error 44, from 69 to 79, and then we ran it in a couple run for a longer period to study the snowbands. But we only for these snowbands we did not a continuously simulation, but we only started like the January of the year the snowband occurs, or the January before if it was like in late winter, early winter or so. So when the snowbands occur over the Baltic, we found out for these events I showed before that we mainly have the same sea level pressure system. So we have like this high pressure system over Scandinavia and a low pressure system over southern Europe. This is basically the same for all snowband events. And here you can see there are some slides missing. Plus, so I thought it would be nice to work with a PDF, but it does not work so well. Sorry. So Okay, what I wanted to explain in this slide is that we did some runs which we call CCLM. This is the standalone coupled runs where we only force with error interim. Then we did do 2 coupled experiments. The one where we used the fully coupled system with the ocean model, but we employed another experiment where we forced the atmosphere model with fixed SST, as we call it. That means we did a monthly mean over the SSTs and passed that on to the atmosphere to see what the atmosphere is doing alone, to have a feeling what the ocean is, what the impact of the ocean is in the coupling. So this is, I just show some pictures of 2 snowband events. This is the one of 87, and on the top panel you see the sensible heat flux. And you see the 3 different runs. So on the left-hand side you see the standalone Cosmo CLM, what it's doing with the sensible heat flux. So as expected, you get these really high heat fluxes. So that means like the ocean is passing on a lot of heat and also humidity to the atmosphere, to the wind which goes over the surface. In the fully coupled system, you see also this high heat flux is going into the Gulf of Bothnia and Finland. In the run where we do the fixed SST, so we have this mean SST, monthly mean SST, so the SST is not changing. The sensible heat flux is also high, but not in all areas as in the other models. So as a result, you get the precipitation and you get the snow bands in the standalone run. You can have it also in the Cosmos CLM, but the fixed SST does not provide such nice snowbands events as in the coupled or in the standalone. So we kind of conclude that that you really need a high resolution, like a temporary high resolution SSTs to model these snowbands very well. These are the slide pictures from another snowband event of 98, and in the top panel I show the differences between the atmosphere and the ocean, temperature differences, and for the standalone run, you see that you also get some of the strong differences in the Gulf of Bothnia, but the nicest differences you really get in the coupled run. Whereas in the run with fixed SST, you barely see any of these large values. So this is also coming out in the precipitation, then that you get this nice precipitation band in the coupled run. I must admit, there are also like from the other events, there are also like examples where it doesn't work out so well. But generally, the runs with CLM fixed SST, they do not give such good results for the snowband events. So these are results which are already written up in the paper and it's under review. But I brought also some newer results which was not in the abstract, but I thought it's nice to show what we are currently working on. And this is also with the coupled model. We work with the same grid, and here we try to do some decadal runs. So in Germany we have this program which is called MiClip, which is focused on decadal predictability, and the project already started in the second phase now, and we started these runs last year, where we want to follow the same outlines as it was done in the MiClip first phase. So the idea with MiClip was that you have a global atmosphere model, a coupled atmosphere model, which is MPI-ESM, which does the decadal prediction, and we at Deutsche Wetterdienst, we did the regional downscaling of these results, and so we have a bunch of regional downscaling runs which were done with the atmosphere-only runs, and this so we kind of followed this outline with our coupled runs that we later can compare these experiments with the MiClip outcomes. So we use the initial and boundary conditions from the MPI ESM global run, and we initialize the model at the beginning of each of the 5 decades and let the coupled simulation run. And we calculated the added value following the approach of De Luca, which was, yeah, okay. So what is generally behind this? So we do the temporal mean for the uncoupled run and for the coupled run and compare it to EOPS data and get a value which is called the real added value, where we hope to see if there is an added value in our coupled simulations. And so for the 5 decades, we find that actually in the last decades we get nicely an added value. So each time the values are positive, that means we have an added value. So we have actually an added value in areas which are far from the northern Baltic Sea with the coupled simulation. So, as I just said, this is just work in progress. So we have to take these results and compare them with the V-clip runs, to compare them with the uncoupled runs to see actually where we get added values compared to the atmosphere standalone run. Yeah, I'm almost done. So, and my conclusion, as I said, we can, with Cosmos CLM, with a resolution of 25 kilometers, we're able to capture the snow bands pretty well. The fixed SST has a lower capability of to simulate the snow bands. Thus, we conclude that you need really high resolution error interim SSTs or like a active coupled ocean to simulate the snow bands. And for the future protection, then it's inevitable that we use a coupled ocean model. So to have this, to get these extreme events as snow bands for the northern Baltic Sea ride. So for the decadal predictions, we see some added value with a coupled simulations, which we have to investigate in detail further. So what is work in progress? So I'm part of the Cosmos CLM community. This is the community around the atmosphere model, and together with some other groups in this community, we developed what we call a unified interface to couple different models to Cosmos CLM. So this is, I think it's pretty nice and powerful that we can actually decide if you want to couple a different land model, which is already coupled, or couple an ocean model or not. And in this framework, we already coupled our Northern Baltic Sea model to the Cosmos CLM, but we are also able to couple the model of the Mediterranean Sea, which I also participate in coupling together with a group of Bodo Arons at Goethe University. And we also collaborate with Hagemann at HZG over the Cosmos CLM community. So for me, in my position at the moment, it's a really nice and powerful network of people working all with the same atmosphere model, and we are pretty well connected. And another point is also that we need to include a river runoff model, which we're also working on at the moment. And there's another PhD position which should look at the lateral boundary conditions in the ocean and atmosphere. So we have like really this nice setup. So the next steps will be to really go and run for the evaluation runs with the 1 or 2 ocean models coupled. We have to decide what we do first. And yeah, so this is our work in progress. Thanks for listening.
We have time for one question. Erik.
Very interesting. We have tried sometimes to look at snowbands also with the RCA model, and you said that you have a good match here at 25 kilometers. I think we have problems even at 12 kilometers to get the intensity correct of these events. Snowfall amounts are way too small all the time, and I'm wondering, have you looked at the intensities also in the presentation here?
We looked at the intensities from the model side, but we really had a hard time to get the data to compare it with. So we have no background where we can say, yeah, we have this event and this amount of snow, and we can compare it directly. So if you can provide us with a source for more data, so we can actually look at the events itself. So
my other question also, I mean, the events, they are quite specific, and
yeah,
in order to capture them and get them in exactly the right place,
yeah,
then you probably need to have maybe some nudging of the model. And I looked at the 98 case there, and the snowband is there, but it's misplaced in geography by some 100 kilometers or so, so you will never capture that in the observations unless you do something with the model to tweak it to get it in the right place. So you have not done anything like that?
No, we have not done, but it would be really interesting to do that, yeah.
Yeah, thank you very much. There's also a nice one in Germany in 78, 79 with 2.5 meters snow in northern part of Germany, which I think you can get the data to validate. So I think this is really important.